AP practice exam review. We're going to start with question number 3 of the free response. And this one looks like a kinetics problem. We have this reaction right here. And let's see, we have some data. Over time, the concentration of the reactant decreases, what we'd expect. How does the rate of appearance of N2 compare to the rate of disappearance of N2O5? So this is not a fancy calculation one. This is just one looking, oh, it's mole ratios. As this disappears, for every 2 of these, we get 4 of these. So essentially, the ratio of 2 to 1 will have, so looking at the stoichiometry, for every 1 of the N2O5 that reacts, you're going to get 2 NO2 produced. Okay, next question tells us it's first order, and then we're supposed to create a graph and plot concentration, some function of concentration versus time. All right, so when we plot this, we're going to take our data, but with 0th order, we'd plot concentration versus time. With first order, we plot the natural log of concentration versus time. With second order, we plot 1 over the concentration versus time. When we plot the natural log versus time, we should get a negative slope. And that's what we get right here. So I'm going to go back here a little bit and just look at our values that we had. Notice I took these amounts and then I took the natural logs. Then I'm going to plot these numbers on the vertical axis with these numbers on the horizontal axis, and it'll look something like this. Now, unlike the concentration absorbance curve, it definitely doesn't cross through 0, 0. And this looks a little better. We got 500, 1,000, 1,500, 2,000. I think the increment drawing looks pretty good. And we have these different points. So with this question, you would be asked to label these different axis things and then actually draw the line with the points that you have. Okay, oh, I did see one error here, kind of subtle. Just looking here, should have equal increments. So negative 2.2 to negative 1.9 is 0.3. Notice 1 to negative 1.3 is 0.3. Notice this should be negative 1.6. Okay, everything would be equal increments then if this were negative 1.6. So I didn't catch that originally, but that looks like a typo or an error in this book. Should keep the increments the same. So now we're asked to find the rate constant for this, and we can use, and you can get this from your key, the natural log equals negative KT of this. I think on your equation guide will probably say this minus this thing here will equal negative KT, but I like to put it in the line equation form, y equals mx plus b. So I know the slope is going to be negative k, and I think that's probably you can certainly go ahead and try a couple examples and plug it in. I like to go through the slope and just taking my values from the table, and then subtracting. I think this was the time and these were the natural log values, and I subtract, I get a negative number here, but slope is a negative k, so a negative negative, I should get a positive value for k, and I do, even though it's toward a 10 to the negative 4th, which is a small number. How about units? Okay, if it's first order, it's going to be seconds negative 1 or minutes negative 1 or whatever that time is. Okay, so rate in 0th order would be molarity per second. First order, it's just per second. Second order, it's per molarity second. Third order, it's per molarity squared per second, and so on. But that's what we have here. So make sure you know how to get units on this rate constant or rate law right there. Okay, let's see. What do we have here? We have, in terms of units, if rate is this, then, oh, I'm sorry, we already did that one. Let's go to the next question. What would be the concentration at there? So if you have to solve for something at a particular time, You have everything but one thing you're missing, so you can go ahead and solve that. And if it asks for the half-life, you certainly could plug in values that represent this is half as much as this, or you could just use the formula from your equation sheet. The half-life equals 0.693 over K, because you know the half-life and you know K. That's what divided by per second leaves you with a time in seconds. So that seems to match out. And what about adding a catalyst? A catalyst provides a different energy pathway. It's a new reaction, so you will get a different K value. In fact, it'll be a higher K value because it's a higher K value means a faster reaction. So you are going to get a different rate constant value because it is a different reaction and it's going to be faster. So what's going to happen is catalyst speeds up the reaction and the rate of disappearance of your reactant will be quicker or increase. The magnitude of the rate constant will increase. I guess we talked about that because it's a different pathway, different uncatalyzed, it's a different reaction path with a higher K. And then the half-life will be less because it's going to take us less time to get there. Probably the easiest way to figure that out is if my K value is bigger, I can go to this equation. If my K value is bigger, it's in the denominator. My half-life is going to be smaller. So that would be this question number 3 right here. I think I'll look at number 4 as well. This is one of the shorter questions right here. And let's see, consider the Lewis structure for the following 4 molecules. And what do we have? So I don't like this question. I think it would be hard to rank all these 4. I don't think you have enough information to do that. Okay, there's probably one with the most that you could determine, and then it's somewhat hard to figure out. So in that sense, I don't think it's a real good question. On the other hand, I think there's a lot we can learn from it. And I would identify the forces. So they all have London dispersion forces. Okay, with carbon hydrogen, they're generally going to be nonpolar. Notice we have hydrogen bonding in 2 of them. Okay, notice nitrogen, oxygen, or fluorine, where the hydrogen is actually attached to the hydrogen. Okay, so here would be hydrogen bonding, here would be hydrogen bonding. This would not have hydrogen bonding because hydrogen is not attached to the oxygen. All right, so these 2 are the only ones with hydrogen bonding. Okay, so that seems to mean stronger molecular forces here. But as far as LD forces, the ones that are going to be the strongest are the bigger ones. And that would lead me to think it's these 2. Well, I'm thinking this one has both hydrogen bonding and more LD forces. So I'm probably thinking this is going to be the largest. But then it's pretty not clear cut because this has a lot more LD forces, but this has hydrogen bonding. So and it is quite a bit smaller. So it's pretty hard to tell between these 2. And this could be even, it doesn't have hydrogen bonding, but it definitely's got more LD forces and it's got some polar forces where this one doesn't have. And this one is what it is, has more LD forces than this one. So I think it's hard to tell between these 3. This one I think would have the most. So that's the best I could do with that. And I think it's a poor question. I don't think you'll get one on the AP exam. And if you do, answer it as best you can and then roll on with your reasons. Okay, I kind of wrote that in there, what I thought about that. Let's see. On the diagram, it says methanol. You're supposed to draw the dipoles. And again, oxygen, hydrogen is pointed like this. Now we know these look like these dipoles cancel out, but they don't because this is really, it's what a tetrahedral shape. You got 109-degree bond angle, so it actually looks a little bit more like this. I just thought I'd clarify that to make it clear. And then, we said the N-butylamine is found to have the lowest vapor pressure. So the one with the lowest vapor pressure is going to have the highest intermolecular forces. That's why it's not vaporizing. And that seems to make sense because that was the one we kind of picked right here that had the more LD forces and also the hydrogen bonding. So that's not surprising with that we're asked to do that. So I just link cause and effect to my answer. The vapor pressure rises from molecules overcoming intermolecular forces to other molecules, escaping the surface of the liquid and becoming gas. Okay, hydrogen bonding, and I like this description, large, highly polarizable electron cloud. So it's got those two components. You would have the strongest IMFs, and therefore it would have the most difficult time escaping, leading to the lowest vapor pressure. I thought this was linked really well in that answer there. All right, thank you for watching this. We'll come back with one more video to close this out. Thank you.